please welcome Jael and Cedric Halbronn, who will walk us through their latest findings in kernel vulnerability and lessons from real-world exploitation.
Hi. Hello? Hi, I'm Jael. I'm a security researcher, and with me is Cedric Halbronn from EasySecLab. Today, we'll be talking about 2 vulnerabilities I found in Windows 11. But first, why should you care? Well, these 2 vulnerabilities that I found were probably the single biggest reason as to how I got employed in this industry, and which allows me to do security research full-time. So, if you're new to this industry or looking to get your first job here, I promise you that after this talk, you'll get actionable advice as to how you can find your own vulnerabilities and break into this industry. And for the more advanced researchers in the audience, KTM remains an accessible, complex, yet woefully unaudited attack surface to this day. So I promise you that after this talk, you'll know more about KTM than 99.9% of people, and you'll be well equipped to find your own vulnerabilities in the system. And for those that tune into our OffensiveCon talk, a lot has changed in KTM since over the last 6 months, and we'll be covering that too. Cedric will cover his adventures using AI to find vulnerabilities in KTM.
So what is KTM? So basically, this is a whiteboard that has been used by Windows developers in 2007. So it explains roughly what KTM is. And on the left, you see OB, TX, TM, RM, and EN. OB stands for objects, because basically the different objects in the kernel in KTM are tracked by the object manager. But KTM stands for kernel transaction manager, so it's about dealing with transaction, which is atomic operations. And so transaction, it's an atomic operation, TX. TM would be the transaction manager, so it's basically dealing with the log, for instance, so we can recover from transaction, from errors. Resource manager is about dealing with a resource, like a file or a registry key. And then enlistment is basically a link between a transaction and a resource, a transaction and a resource manager. So basically doing the link. And when we think about a transaction, it will be composed of many enlistments that are part of the same transaction. So this is for the KTM in the kernel. KTM is a component in the kernel, but it's actually used by other components like TXF and TXR that you see on the right, which stands for Transactional File System and Transactional Registry. As you can imagine, basically, Windows uses their own KTM APIs for doing transaction at the file system and registry level. And the last thing I want to talk about is the Win32 API. So because we're looking for local privilege escalation vulnerabilities, we want to make sure we can reach them from userland. And so we have APIs from userland to do syscalls and interact with KTM. Okay. So this is kind of the developer there is a video where it shows this diagram explaining what KTM is, which is quite nice, actually, from the Vista era. So anyway, this is kind of the workflow if you want to create the object in the kernel. So you create a transaction manager, then you create resource manager to deal with the different resources, so for instance, files and registry. Then you create a transaction, which is basically just, you don't even pass any arguments, it's just an object that tracks the transaction, and then you create enlistment that are the different operations that are part of the transaction. So in the kernel, this is the kind of object you end up having. So we have the transaction manager. So most of the structures here are self-explanatory. K-transaction, for instance, for a transaction object. The only one that maybe is not super clear at first is KTM, because it's actually the transaction manager. It's not a structure to track the KTM state, but it's like KTM in the actual component. But KTM is actually the transaction manager. So we have the transaction manager, resource manager. One thing we can see is that there is a linked list of enlistment associated with a given transaction. And there is also a linked list of enlistment associated with a resource manager. And so for a given resource, we can have several transactions, obviously, associated with the same resource manager. Okay, so let's go back to kind of the history of KTM to give you an overview. Because we want to be doing some vulnerability research and look at KTM in general. So in Vista, KTM was released, even though I didn't hear about it until probably 2019. But basically, in 2007, Vista was released. Then there has been a few bugs in syscalls found by Project Zero, among others. But there was no like real public exploit full chain that would allow you to elevate privileges, as far as I know. There is one bug that has been released in 2018, which is a use after free. It was quite interesting. It was exploited in the wild. And actually, we did some research on this bug with a colleague at that time. And the bug, there was no POC or even like a binary on Aristotle or anything that was containing how they exploited it. So we did our research on that. There are some blogs online as well and presentation. In 2019, some people were using like transactions in order to evade AV by creating files that are part of the transaction that don't really exist at the file level, but where you can do certain things. And then there are some bugs as well in 2023, but again, nothing where you get a full chain to exploit the kernel. And then in 2024, I started delivering a training on exploiting the Windows kernel, and one of the main thing of the training was to actually exploit this bug from 2018 from different angle with different strategies to explain how to exploit the Windows kernel. And so Jael followed this training, and then a few months later, he found 2 use after freeze in the Windows kernel in KTM. So that was like, oh, that's cool. So we'll talk about that. And more recently, we're like looking at the recent changes in KTM, because there hasn't been many recent changes, but there hasn't been a lot of changes over time, but actually recently there have been some changes. So we'll look at the different changes that have happened recently in this last summer. And we'll do a little bit of vulnerability research using AI after that. So if we look at the bug, we'll go over roughly kind of bug 1, which is like the one in the wild, then bug 2 and 3 found by Jael, and then some bugs in the patch diffing before talking about our own new research. So bug 1 was basically, and we don't want to go into too much detail because we can always refer to other previous presentations. But just to get an idea, the idea is to find some common pattern. So the bug from 2018 is basically about recovering a resource manager. And it's about the fact that we are going to go over a linked list of enlistments associated with a resource manager. And so the way it works is that, without going too much into detail, you don't need to read this code, but basically in the block in black, what it's doing is checking the state of the enlistment, checking if it's finalized, and if it's finalized, it's going to set a Boolean, but if it's not finalized, it's not going to set this Boolean. And then it's basically going to do some work, and later, if the flag is set, it's going to assume the enlistment was not finalized, or it would assume it's finalized, and it would actually use if it's finalized, it means it's actually freed, it's actually finished, and it's going to basically go back to the head of the linked list to start reprocessing the enlistment from the start, because the enlistment is freed, so it's invalid. But if it's not finalized, it will just use the next pointer from this current enlistment. But you can see a problem here. It's like basically it could be detected as non-finalized, and then there is maybe a way to free it in between, and then based on the flag, it's going to assume it's not finalized and then reuse a freed chunk. So it's a use after free. So one tip we want to mention when doing research in general is just be curious, because you want to understand how things work, and just in order to improve your understanding of things. And so when we're doing the research trying to exploit this vulnerability, we were documenting all the different objects in the kernel, because there hasn't been any public research. And so there are like K-transaction, K-resource manager that are structures defined in the kernel, and each structure has an ID, an identifier, which is a cookie, but it's an ID that ends with like 1, 2, 3, 4 for all the different objects. And so we're documenting all the different objects.
So earlier last year, Earlier last year, I took Cedric's KTM course. While doing so, I came across this table of object cookies. Instantly, my eyes were drawn to the two undocumented cookies at the bottom, cookie 5 and cookie 6. According to the table, these corresponded to a protocol address information object and a propagate request object. So, I got curious. I did a quick Google search for the value of cookie 5, but found nothing interesting. So, I took the KTM driver and I placed it in IDA, and I did a quick text search for the value of cookie 5. I got one result, TM register protocol address information. And I just started manually reversing the cookie 5 object line by line in assembly. Occasionally, I would add little comments about what I thought each code block was doing. And it's worth pointing out that at this point, I wasn't looking for vulnerabilities. I didn't even know if this code path was reachable. All I wanted to know was, what do these overlooked cookies do? And it's this methodology of not trying to find vulnerabilities upfront, but instead seeking to deeply understand the underlying code base that I picked up from a talk given by Satoshi Tanda. Do not find bugs, bugs will find you. And I spent about a week just manually reversing the cookie 5 and cookie 6 objects this way. And when I was done, I just started playing around. I wrote a little POC to explore the functionality of these objects. And once again, at this point, I wasn't looking for vulnerabilities. I was just trying to merely understand the extent of the functionality of these objects, as well as the intent behind the developer that created them. And in doing so, I came across 10 promising ideas for potential vulnerabilities in KTM. Unfortunately, all 10 were failures. Now, you don't have to read every line of this slide, but I've added it because I think it's very important to show what the reality of vulnerability research is really like. It's not very glamorous, and oftentimes it's a lot of repeated rejection, failure, and paranoia. And with each rejection and failed idea, I grew more and more frustrated. Looking over my diagrams, I found one edge case, one diagram I created. Looking over my notes, I came across a diagram I created while trying to pinpoint some edge case ref count / race condition vulnerability, and it looks eerily similar to a red string conspiracy diagram. So it's really hard to overstate just how much of a mental game vulnerability research really is. When I first joined this industry, I just thought that everyone up on stage is just so much better than me and that they're just too good to have ever failed. But that couldn't be further from the truth. As everyone in the audience today can attest, we've all failed more times than we can count. And this wasn't my first time reversing the KTM driver. This was my third. My first and second times both ended up in failure, and I just never bothered to tell anyone. Whenever you're reversing a component, you're constantly being told that your understanding of the underlying code base is wrong. But that's okay, because you only have to be right once. Vulnerability research is a lot like playing baseball with no strikeouts. You can constantly swing in silence until you get a home run. And what I found really helps is exercising regularly. Late one night after my 10th failure, I was running on the elliptical when an idea came to me. What if I freed one object while another object was in use? Initially, I dismissed this idea. But I told myself, I already have 10 failures, what's one more? So I went home and I wrote a POC and I tried it. And I got a blue screen of death. So this is my very own first vulnerability in the Windows kernel. And as you can see from this snippet in my notes, I was absolutely ecstatic when I first found it. So what is the cookie 5 object? The cookie 5 object is a protocol. It's created when we call NT-register protocol address information ext on a resource manager handle. This function allocates and initializes the protocol object, and in doing so, it adds this protocol object to the resource manager's protocol list head linked list. Importantly, when we free the resource manager, all entries in the protocol list head linked list are freed as well. Now, there are only two important fields in a protocol object. The first is the protocol GUID field. Now, this is just a unique identifier for each protocol, so no two protocols should ever have the same protocol GUID. And the next important field is the resource manager field. Now, this is just a pointer to the resource manager that registered the protocol. Finally, there's an interesting kind of protocol known as the promoting protocol. And the only difference between a promoting protocol and a normal protocol is that a promoting protocol has this special static GUID here. Now, you don't have to remember it. It's just some static value. But you just have to know that if a protocol has this special GUID, then it's known as a promoting protocol. Next, let's take a look at the cookie 6 object. The cookie 6 object is a propagate request. It's created when a transaction undergoes something called transaction promotion, which calls this TMP allocate propagate request function. This function allocates the propagate request, and there's only one important field in the propagate request, and that's the resource manager field. However, unlike the protocol object, this resource manager field of the propagate request is initialized to null. Now, after being allocated, this propagate request is dispatched in this function called TMP dispatch propagate requests. Let's take a look at it right now. So, the first thing that this function does is that it finds the promoting protocol. Now, we'll remember that a promoting protocol is just a protocol with that static GUID that I mentioned. Next, the function finds the function sets the propagate request resource manager field to the promoting protocol's resource manager field. Now, can anyone spot the vulnerability here? Okay, so after we find the promoting protocol, but before we read the resource manager field of the promoting protocol, we can actually free the promoting protocol here. Let's take a look at how we do that. We'll remember that when we close a resource manager, all entries in its in the protocol list head linked list are freed. So this is done through the TMP close resource manager function, which is the close procedure of a resource manager object, and is called whenever we close the handle of a resource manager. And it calls TMP delete protocol on each entry of the protocol list head. Now, what this means is that we are able to free the promoting protocol and reclaim it with a name pipe with data we control. So we poison the resource manager field of the promoting protocol. So when in TMP dispatch propagate request, it uses this poisoned resource manager field value in KE wait for single object, KE release mutex, and TMP set notification resource manager, we're able to point this poison resource manager to user mode and get a write zero primitive to null the previous mode of an each thread to escalate our privileges. There are two constraints to reaching this vulnerability. The first being that the exploit needs to be ran on a clustered disk. And the second being that only the KTM RM service can register a promoting protocol. Now, please note that the second constraint is a legitimate security boundary, and it's the reason why this vulnerability requires high privileges. For the purposes of the demo, for the upcoming demo, I'll be using this windebug command to patch this function to emulate a clustered disk, and use this windebug command to patch this function to emulate running within the context of a KTM RM service. So let's try it right now. Okay. Let's give it a second. Like I mentioned, we'll be using these two windebug commands, to patch to emulate the clustered disk and the KTM RM service. Okay, this is actually a good sign because we didn't crash, but unfortunately, it looks like there's some thread issue. Let's try one more time. And as you can see, we've achieved a system shell. Now at this point, I was all smiles. I found a bug, or rather, a bug had found me, and I was ready to move on. However, when I told a friend about this, he advised me to continue looking at KTM. And I'm glad he did, because I ended up finding another vulnerability in KTM. Now at this point, I have a whole nother story of how I found this other vulnerability, but unfortunately, because of time today and the new content we're about to present, I'm not able to share that story. Thankfully, I've already given that story in OffensiveCon, and I'll link this video at the end of our slides, and you can take a look at that soon. So after giving that talk at OffensiveCon, we were graciously invited by the POC crew to give an updated version of this talk here in POC2025. So a few months before the conference, I took the KTM driver and I put it into idle free to see if there were any changes. And what I saw was this like trash fire, right? There were so many changes to KTM. Now let's take a look at the first one. Oh, but fair warning, before I continue, I have to give some warnings, right? Everything I say going forward is my best effort at patch diffing and root cause analysis. Because I didn't find these vulnerabilities myself, I could very well be wrong about my analysis of those. Furthermore, I can't know for sure which CVE belongs to which vulnerability. So please take everything I say from this point onwards with a healthy grain of salt. So let's take a look at the first vulnerability. Now this is a use after free in the kernel transaction manager, and the description basically says that it requires an attacker to win a race condition. So I diffed the version of KTM before and after the patch, and there was only one change. So I'm pretty confident it's in TMP initialize enlistment. Now this patch to TMP initialize enlistment is pretty simple. It just adds this reference to the transaction manager at the start of the function, and it adds a dereference to the transaction manager at the end of the function. And honestly, I was like really confused. So at first glance, it looks like this vulnerability probably involves being able to free the transaction manager while in another thread, while the main thread is in TMP initialize enlistment. However, this doesn't make sense, because to free a transaction manager, you have to first free the resource manager that belongs to the transaction manager. But if you could free the resource manager while the main thread is in TMP initialize enlistment, well, you have your own vulnerability right there. And furthermore, the patch that Microsoft introduced would not solve this ability to free a resource manager. So if it's not, and furthermore, whatever the patch does, it doesn't account for the fact that in TMP initialize enlistment, after dereferencing the transaction manager, you can actually call TMP forward commit transaction and TM rollback transaction ext in certain cases. And these two functions actually access the resource manager and the transaction manager. So however you're able to free any of these objects, Microsoft doesn't think you're able to do so within these two functions. And if it's not a use after free of a transaction manager object, then what could it be? Well, it could it be a use after free of a child object of the transaction manager? I took a look, but I don't see that kind of child object that you could use after free. And most importantly, before the patch, we were already referencing the transaction manager. All the patch does is add another reference to the transaction manager. So why would one reference to the transaction manager allow you to free the child object, but two not allow you to? So it doesn't make sense to me. Secondly, you can actually hit this TMP initialize enlistment function if you go through if you do something called enlistment migration, and you go through this code path that creates something called a CRM enlistment. However, this code path is really restrictive, and once again, I don't see how it's any different from creating a TMP, creating an enlistment by yourself. Finally, maybe this has something to do with TMP recover. So you can actually recover KTM objects from a log file, and maybe you're fuzzing like the log file itself, and then you call it to be in a weird state. But again, like this begs the question, what are you used after freeing? So I'm sorry to leave you guys with more questions than answers, but for this vulnerability, I don't really understand how it works. Next, let's take a look at the next vulnerability. Now, according to Microsoft themselves, they call this the resource manage ref count mismatch. And let's take a look at how this works. Let's take a look at the patch. The patch is pretty simple. It adds a reference to the resource manager before this OB insert object. And if you fail this OB insert object, you call the close routine of the resource manager, which is TMP close resource manager. Now, at first glance, I was thinking, and I was like, okay, this looks to me like a memory leak where the developers didn't account for the fact that you could fail OB insert object. And as a result, maybe they forgot to free the resource manager. And so maybe if you can call create resource manager a bunch of times, failing OB insert object in each iteration, you could create a bunch of unfreed resource manager objects, exhaust all the kernel resources, and crash the system. So I quickly found out how to fail OB insert object, and I did a quick test. Unfortunately, when you fail in OB insert object, you dereference the resource manager, and the ref count goes to 0, and you end up freeing the resource manager. So there isn't this like memory leakage / resource exhaustion angle. But I did a little bit more thinking. What if you call open resource manager after the resource manager has been initialized, but before you fail in OB insert object? Well, open resource manager Open Resource Manager should return you a handle of the resource manager, and OB insert object should fail and free the resource manager. Does this mean you get a handle to a free resource manager? Let's take a look. So we're just gonna run, and before I show you the demo, so what I'm gonna do is I'm gonna create a resource manager in one thread with a desired access value of -1, so I can fail in OB insert object. And you'll see that I'm creating this resource manager with this default RM GUID. Now, in another thread, I'm gonna call open resource manager with that same GUID, trying to open that. Now let's take a look at what happens. So I'm running the POC, and as you can see, instantly we crash. And let's take a look at why we crash. Okay. So as you can see right here, if this will stay still, okay, it won't. But we have something called a reference by pointer vulnerability. Basically, we crash because we're trying to reference this object, and I can tell you right now, this is a resource manager object, and it has a ref count of 0. And as a result, you crash because, and let's take a look at, the text size is a bit too big. And let's take a look at the faulting thread. Now this is thread 2. This is thread 2 that's calling open resource manager. And as you can see, it finds the resource manager in TMP namespace lookup, and it tries to reference the resource manager with a ref count of 0. Now let's take a look at the thread 1. And as you can see, the call stack of thread 1, this is the call stack that's calling create resource manager. And as you can see, we fail in OB insert object, and now we dereference the OB the resource manager to a 0 ref count, and now we are blocked in TMP delete resource manager. As you can see, we are waiting on the mutex of the transaction manager that the resource manager belongs to. Now, the reason why we are blocked is because thread 2 is actually holding this mutex. So as a result, if we just take a look at the object right here, the resource manager, we'll see that it's allocated, it's not free. So there is no use after free. It's just a reference by 0 vulnerability. Yep. Now, let's take a look at the next vulnerability. This, according to Microsoft, is called the enlistment security init. And the patch is pretty simple. It adds this hex 100 flag to the enlistment after OB insert object. Now, importantly, OB insert object is what creates the enlistment handle. And this hex 100 flag that's applied to the enlistment is only used in, as far as I can tell, one other place, TMP lock transaction. Specifically, if an enlistment is used in this function without this flag, will fail. If an enlistment has this flag, then what we'll do is we'll call OB get object security to obtain the security descriptor of the enlistment, and then we'll do some work on it. So this is probably trying to stop you from calling TMP lock transaction on an enlistment that hasn't had its security initialized yet. So when does the security get initialized? Well, the security gets initialized during OB insert object. What this means is that we have to call TMP lock transaction before we obtain an enlistment handle. And that just doesn't make sense to me, because the ways I know of to call TMP lock transaction, for example, pre-prepare complete and prepare complete, both require the enlistment handle. So I'm not sure how you can call TMP lock transaction before you even have an enlistment handle. And what if, astute viewers in the audience might be thinking, what if you do the same trick you just did with Resource Manager, where you just call open enlistment to obtain the enlistment before you finish OB insert object? That's a great idea. Unfortunately, you return status invalid parameter, so that doesn't work. Lastly, let's take a look at this vulnerability. And so this is not in KTM, it's in MSDTC, and it's an information disclosure vulnerability due to an integer overflow. Now, I found the vulnerable function. As you can see, it's getNext var item within bounds, and I would say the patch speaks for itself, right? The pseudocode is very legible, and you should be able to understand it instantly. So I won't proceed further. Thank you. I'm just kidding. So the this whole time, I've been writing the pseudocode by hand, but I thought for the last one, like, hey, why not let's test if ChatGPT can write decent pseudocode. And surprisingly, it does. Now, it might still look a little bit complicated right here, but don't worry. At this point, all you need to do is just read the lines highlighted in red. These are the patches. And as you can see, at the top, there's a patch to check if the length is greater than hex FFFFFC. And when they calculate a line length, so a line length is just length plus 3, so just to round up to a multiple of 4, they check if a line length is greater than hex FFFFB. And if any of these checks are true, we just bail out the function. So they're trying to stop an integer overflow here. Now let's walk through some example versions of lengths to get an idea of how this function works. Let's say we supply a length of hex 1, right? A line length will be 4 because 1 plus 3 equals 4. And you'll see that cursor pointer will now point to 4 bytes ahead of where it was. And from this little diagram here, you can see that cursor pointer was pointing to the length at the start, and now it's going to point to the next length, which is 4 bytes away. And this is all totally fine and normal, and it's how the function is meant to be called. Let's take a look at what happens if we pass -1, which is OXFFFFF, as our length. Well, the align length is going to be integer overflow to 2 because -1 plus 3 equals 2, and the cursor pointer is now going to be incremented by 2. So what's going to happen is that the cursor pointer is now going to point within itself. It's going to point within this 4-byte data that it should never point to. And so you're probably asking now, okay, where's the POC? Well, it's here in Seoul, right? I'm just kidding. But seriously, I don't know how to reach this function, right? So it's in MSDTC, which means you probably have to call it through these DTC interfaces, but none of these interfaces seem to like immediately call this function. So it's probably something very stateful / nested. And yeah, so unfortunately, I don't have a POC, but I can probably tell, I can just opine and say that the bug probably allows you to leak data / pointers within MSDTC by calling this function multiple times. And you could chain this with another bug to get code execution within MSDTC. And you can even chain it with the TMP dispatch propagate request bug that I showed as my first demo, which required you to be within the security context of MSDTC.
So we've got a good understanding of previous vulnerabilities and more recent ones that have been patched. So one thing we're going to present here is basically our journey in analyzing KTM from an AI LLM point of view. I think the reason we're presenting it is because we think it's quite interesting to see the kind of methodology and results we get with AI. So we're more interested in the methodology than the results. So the other thing I want to say first before I go through the slide is that because the LLM, we're asking lots of questions, all the statements that we show in this presentation, some of them might be false, but the reason we're showing them is just to show the methodology, and also our main goal was to really focus on finding bugs, not on actually trying to understand everything the LLM was saying. But we basically use the LLM output as some information to dictate our next step, and so some stuff we didn't check because we thought intuitively it was wrong or whatever, and we just followed our instinct. So I'm just going to explain roughly what tool I used. So I've used Codex, which is basically an OpenAI tool, AI agent that basically works with GPT. Very good. You can plug it with any LLM, but it's very integrated with GPT. And the idea is it's a reasoning agent, so you can ask questions and it's going to go with a plan and then do certain sub-step in order to reach your goal. And it's even going to propose you some new steps of things it thinks you should do. I've plugged it to Ghidra using an MCP server. So we talked about it earlier. But basically, it's a way to a standardized way to expose a tool to an LLM. And so it's running in Ghidra, and so Codex is able to query Ghidra for decompiler output or other things, or even modify the Ghidra context. In Ghidra, I'm loading a vulnerable TM.sys, which is basically vulnerable to the first bug exploited in the wild and the two bugs that Jael presented that he found in between. And the reason for this is because it's going to allow us to train the LLM with some common pattern. Then I'm loading into a target VM the vulnerable tm.sys, and I've attached a WinBag debugger. So this is mainly for debugging manual analysis. I didn't have an MCP server in WinBag, but that would be something we could do. And then I also have RedSync, which is a great plugin to synchronize WinBag and Ghidra, so I can just easily debug in WinBag, and it will basically show me the decompiled code in Ghidra. I can debug in WinDBG and see the decompiled code in Ghidra. So I have my environment with vulnerable KTM, so now I can train the model with common patterns. So I feed the model with like the blog posts, the five blog posts series I wrote with a colleague in 2019 after exploiting the bug. And then I also feed the two write-up that Jael wrote when he was finding and exploiting the bug in 2024. And that's basically the bug reports that he sent to Microsoft. And I say, analyze the write-up and give me an understanding of your vulnerability, of the different vulnerabilities. So here, I'm not expecting you to read, but I just want to explain roughly the structure of this slide, because all the future slides, every time I query the LLM, it will be the same kind of layout. So the top is basically my query, my prompt, what I ask the LLM, and then I'm not showing all the output, but kind of the results of what the LLM is giving me. And in this case, it's giving me like defining what kind of vulnerabilities it found in the different write-ups. And so that was pretty cool. It was kind of correct. The reason I asked this in the first place is because it allows me to confirm that the LLM is not going into some kind of hallucination mode where I'm not going to continue my research because it's totally wrong on what it's doing. So I was like, cool. So then the other thing I did is I basically asked it to check over Ghidra if the exposed tm.sys was vulnerable to these three vulnerabilities. And again, the assessment was correct. Sorry, it identified that the tm.sys had vulnerable code to these three vulnerabilities. So I was like, oh, cool. Looks like I have an environment I can work with. The last thing I wanted to check is I added the 3 proof of concept and some crash dump files to give some kind of exploit or POC to trigger the vulnerabilities. And the reason I did that, again, is to train the model and see what it comes up with. And its analysis was correct. Again, it was like detailing how we would trigger the bug and how we would maybe free the enlistment from another thread using the same kind of method that we described earlier. So I was like, cool, I have my environment. Now it's to do some kind of bug hunting or vibe hunting, like we said today. So the first thing I did is I asked the LLM, can you please, so actually it's not really bug hunting, but here it's again checking with the vulnerable tm.sys, can you find one of the bugs that has been patched in 2024? And I've used TMP initialize enlistment, which is one of the bugs that was described by Jael in the patch diffing. And I tell it, can you please find vulnerabilities in this specific function? But unfortunately, it didn't find any vulnerability. So I was like, maybe that's not that good. But I still decided to move on and not investigate this because I knew it would have been patched anyway. But it was quite interesting information. So now I'm ready to do some research. So what I'm doing is I'm basically updating tm.sys to the latest version, Windows 11, in Ghidra and also in WinBag. And I'm just going to do some research. So I started analyzing KTM, and one of the functions that I wanted it to look at, among others, obviously I'm not going to explain everything I did, but TMP log transaction. So the reason I'm presenting this one is because it actually said there is a potential vulnerability. And I say potential, sometimes I'm going to say maybe it found a vulnerability, but every time I say I find a vulnerability, it's actually a potential vulnerability, just because we're still trying to figure out if the LLM is hallucinating or if it's a real bug or whatever. So it looks interesting because it says it's a race condition, and it's when it's trying to parse a linked list of enlistment associated with a transaction. So it's quite interesting because if we go back to our initial bug in 2018, the one in Recover Resource Manager, it was basically a linked list of enlistment associated with a resource manager. But in this case, we're actually in a scenario where it says that it doesn't lock the transaction mutex, but actually it's going over a linked list of enlistment. So we're like, okay, that looks kind of similar-ish bug. It's cool you found it. So I was like super excited. I was like, okay, go for it. Move. Don't check anything. Just vibe hunting. Keep going. And I was like, create a POC, and I want to trigger this bug. So I was like, okay, cool. Please create a POC file that would allow me to trigger the bug in a TMP log transaction. So I was like, okay. And so, unfortunately, when I tried to debug, it wouldn't actually work. And so the reason is, what happened is, in the case of, if we go back to the bug from 2018, the reason there was a bug is because in TMP Recover Resource Manager, oops, okay, no, it's later. So, no, I don't have it. Okay. So the thing that does happen, oh, sorry, it's because I'm not hitting the right button. Yeah. Okay. So, let's go back. So, there is a potential bug in TMP log transaction. I create the POC, and now I trigger the POC. And when I trigger the POC, what happens is it doesn't even reach the vulnerable function. So I'm like, that's not great, right? So in this case, I went into some kind of manual mode. I was like, okay, I can't trust the LLM anymore. I need to do it myself. So what I did is I went into manual mode where I was like, I'm going to understand the POC it wrote. I'm going to figure out why it's not triggering the bug, and I'm going to fix it. And it turns out, because of the knowledge I had on KTM, it was quite easy for me to do, because I could figure out that instead of calling commit transaction async, it would calling commit transaction. And I know from previous research that I was never able to trigger anything using commit transaction. It was better to use commit transaction async. So I fixed that, and now suddenly I reached the vulnerable code. So I'm like, okay, cool. But then I do a lot of debugging, and when I try to have two threads, one that actually trigger the vulnerable code and the other one that tries to free the enlistment, so there is a race condition, then the one that tries to free the vulnerable to free the enlistment is not able to free the enlistment. And the reason why is because it can't acquire the transaction mutex. I was like, okay, that's not good. Let's try to understand why. And actually, it turns out the reason why it's happening is because if we go back to the TMP Recover Resource Manager, the reason why there is a vulnerability in TMP Recover Resource Manager in the first place is because it would acquire the Resource Manager mutex, but then it would actually temporarily free it, and then some stuff could happen. We could free the enlistment, and then it would require the Resource Manager mutex, but then the enlistment is freed, but then it's going to potentially reuse the enlistment thinking it wasn't freed. So that's why there was a bug. But in the case of TMP log transaction, it didn't find any lock in the TMP log transaction function. But actually, there is a lock in a caller function that actually locked the transaction. So actually, it's not a bug. And we can't trigger a use after free because it's done correctly. And so what I did is I basically add the LLM. That's what I'm encountering in WinBag. It's locking the transaction somewhere, right? Can you check that for me in Ghidra? And basically, it went over a TMP log transaction, figured out the caller function, and it told me, yes, not in TMP log transaction, not in TM commit transaction, but in the NT commit transaction, it's actually locking the transaction mutex. So I was like, that's cool. And you can see like it's 2 minutes. So I mean, probably it would have taken me the same amount of time in Ghidra to figure that out. But the nice thing is while it's doing its research, I can do other stuff in between, right? So yeah, that's what's happening. The transaction is locked from a caller function. So it's not an actual bug. And what is interesting is that actually all the thing it's been doing, I think if I had to do it manually, I would have gone through the same process. So the LLM actually, the reasoning was pretty good. Oh, sorry, I'm doing the same mistake. So the last thing I did, because I was so close to, like I was understanding very well what the code was doing, is, and the previous bugs that had been patched in KTM, I asked the LLM, okay, I know TMP lock transaction can be triggered from NT commit transaction, or it can be triggered one way. So the vulnerable function can be triggered one way. I can free an enlistment one way. This way doesn't work because the mutex is locked, and I can't free the enlistment because it's locking the mutex. So in both ways. So can you find other path that would trigger the vulnerable function or the free of the enlistment where there is no locking in one way? And I would have done that manually, but it went through the different functions. And it's quite nice because it found different functions to free the enlistment. And I know from previous research that actually these functions, we've used them in different exploits for different reasons. So that was quite interesting. Anyway, it's not a bug. Yeah, too bad. Okay, so again, I'm not going to present all the research. It's more to show the thought process and the tooling. But one other thing we tried is to try to analyze TXF, which is the transactional file system. So it's implemented into NTFS, and it's basically relying on KTM for dealing with transaction at the file system level. So I have my NTFS loaded, and that's what I'm working on now. So analyzing it, at some point, it actually found a potential vulnerability in a function called getTransactedVersion related to an FSCTL, which is basically an IOCTL, but for a file system. And TXF stands for Transactional File System. So I was like, that's interesting. And basically, it's telling us, so I asked it to generate a write-up of the vulnerability that I can investigate manually to try to understand the bug. And basically, you don't have to read it all, but the long story short is that it's trying to potentially read the transacted version, which is the version of the current file, because it's been maybe in different states over a transaction, and it's trying to get the transacted version, like between 1 and 57 if we modified it 57 times. And it's trying to copy some context from the transaction to the resource manager in some structures. So that's kind of our understanding so far. And while it's doing so, it doesn't acquire the transaction mutex. So we think that potentially it's possible it gets the transaction information, and then while it's doing other stuff, we can free the transaction mutex somehow, and then resulting in use after free. At least that's the theory. So then I asked the LLM, can you please write a POC? So it's super fast. It generates that in 1 minute. And then I compile it. It builds. Cool. And then I ask it to, then I run it into my VM. And then it turns out it doesn't do anything because it's not calling the right IOCTL. I'm like, okay. But looking at the code is quite easy to fix because I know the right IOCTL. It's getTransactedVersion, so I can just fix it and trigger the vulnerable function. So now I hit the getTransactedVersion function, which is cool. And so just to give you an idea of the kind of POC that it wrote once I fixed the IOCTL. So at the very top, we're creating a file. We don't use any transaction. Then we close the file. We just want it to be created. And then we open the file again using createFile. But with a transacted context. So it's a create file transacted that's going to hit the NTFS .sys, but in the transacted state, so dealing with transaction. And for that, we need to pass a transaction. So we just create a transaction object beforehand so we can pass it. And then the LLM generated some file operations, like writing a file, flushing the buffer, changing the file pointer from one or the other handle. And then it triggered the vulnerable function. So cool, we reached the vulnerable code. The POC it wrote looks legit from our point of view. So now we want to understand roughly what it's doing because obviously I told you a little bit what it's doing, but to be honest, at that stage, I wasn't sure what it's doing. So I was like, can you write some, okay, so I did it in 2 steps. I did it first, can you write some header file that holds the structures that are used in this function, because I want to reverse engineer this function, and all the structures are private. It's not like KTM structures, they are actually transactional file system structures, and they are not documented. So like, can you look at the decompiled code and write structures? And it did a pretty good job. So this is kind of the final state I have, and it went through several iterations, but I guess the main point is it found like there is like some kind of main file object structure which is related to tracking file object information for a transactional file, and the fs context and fs context 2 hold information respectively for the resource, for the resource manager and for the transaction. So the second one is resource and the third one is transaction, and that's kind of what it's doing. It's trying to get the resource manager context. It's getting the transaction context, and then it's copying some context information to the resource manager context, but it's actually a linked list. So that's cool. We've got decompiled. So we've got structure information. So now I see to help with decompiling the decompiler output. So basically using the git MCP server again, but instead of reading decompiled code, I asked it to rename variables. And so you can see that basically it's renaming the variable, but also it's able to change the types of the different variables. And that's pretty cool. Like honestly, I haven't done much modification, obviously minor fixes, and also some fields that it hadn't done on the first iteration on this one, that would have, you see some reserve field, but I had more reserve field originally, and then I just asked gradually, can you fix this field so I can see it better? And then after a few iterations, this is the kind of output I got without doing much in Ghidra manually. So I was like, that's pretty cool. And so what it's doing basically is that it's going over some kind of versioning, some kind of mini versions, they call that mini version, I assume, and it's going over the linked list, and it's trying to find the one that it needs to return. But because, like I said earlier, the transaction context, it hasn't acquired a mutex, potentially it could reuse it, but it could be resulting in a use after free. At least that's a theory, because we're still trying to triage this bug. It's a potential vulnerability, right? So, then I actually asked it, the LLM, can you please find a way? Because the problem I had here in this linked list is that the linked list was pointing to itself right away. So there was only one element in the linked list. And I needed different mini versions in order to create the context I'm looking for in order to trigger a use after free. And so what I did is I basically ask it, can you find a way to create multiple transacted versions so I can, before I call the IOCTL, so the context is correct when I call the IOCTL. And that's kind of what it came up with. The idea is basically, it's doing some file operation, and in between you call another IOCTL that creates a mini version. And our understanding is that it basically creates a snapshot of the current state, and so that's technically what we want to achieve, even though I wasn't able to confirm it. And the reason why is because after a lot of debugging and trying to understand why this IOCTL wasn't working, the create mini version, it turns out the create mini version IOCTL returns request is not supported. And so generally, when you call an IOCTL, you get access denied or the IOCTL doesn't exist when it's not supported. But here, actually, after debugging, we found out that basically the IOCTL went into an error saying, if it is this IOCTL, return not supported. So okay, why is it still in the kernel? So anyway, also this slide is to show that another thing we asked the LLM, which is, can you please generate a POC, another POC that basically go over every single IOCTL related to the file system for transacted things, and let me know what you can do. And you can see that it called all of them, and some of them are not supported, incorrect function, or handle is invalid. So just to show that this kind of methodology could be applied for fuzzing, for instance. So unfortunately, because we can't call mini version, we were not able to get the state we wanted. Obviously, we tried lots of different other things, calling transacted functions in order to create some context that would maybe trigger the context we want. It didn't end up resulting in something useful, but yeah, that was quite interesting. The last thing I want to say is one thing we haven't tried that we could try is to basically patch in the kernel. So when we do execute the device IO control, it actually call because the function is there, like the handler for the mini version, the create mini version function is there. And so just to call it to make sure our understanding of the bug is true, but obviously patching the kernel to allow a feature is not something that would give us a real bug anyway. So anyway, this is kind of the research. So we didn't find any bug. I think the methodology was cool. Hopefully you enjoyed it. The cost of this research was $25, so it's not that much. This is just to show I had an alert to basically, I didn't know if it would cost hundreds and hundreds, so I had an alert every time I go under £5, it just recharge automatically my account. So this is kind of showing that it was recharging my account a few times. And on the right, you see basically that it used 120 million tokens in this research. And it did an amount of 1,400, like 1,500 requests. And my understanding is that when I do like a prompt, when I query the LLM, underneath, because it's doing all the reasoning, there are several requests done. So maybe it's like maybe 400 or maybe 400 prompts or less, and then it results in this amount of total requests.
Finally, if there's one thing you take away from this talk, is that more than ever before, we believe you can find vulnerabilities. Finally, I know we don't have time for questions, but if you can catch us during the conference and ask us a question, we have a special signed autograph Magic the Gathering card for you. Thank you so much.